are you able to see the screen? Okay.
Yes.
Okay, so like also Philippe mentioned, I'm Daniel Bolojan. I'm an assistant professor focusing on AI and computational design at Florida Atlantic University. I'm also a PhD candidate at the Young Event Kunst, and currently I'm collaborating with Copion Blau, working on the Copion Blau project, which is a project that looks at development of neural networks and the application of these neural networks in architectural design. So over the years, my research interests covered a few research areas, such as complex systems, agent-based systems as generative engines, agent-based systems as social agents, and creative AIs. One recurring theme in this research is the idea of encoding intelligence, or this idea of articulation of a design process in which architectural intention and architectural intelligence is embedded within the emergent process. So early on, while I was still a student, I was very impacted by this quote from Liz Werner, and the way that I started to understand architecture actually I had almost like a sort of shift in thinking. And I started to look in a way at architecture as this kind of idea. The architect is no longer an organizer of matter and space, but a designer of systems with multi-layered components and complex relationships. So I'm saying this because you'll see that some of my work, it's very design oriented, and I'm really looking at aspects of building systems in a way to generate design or to address topics of design. My initial interaction with AI was in the form of statistical learning, which was used mainly to give predictions for agent-based systems, proximity calculations. And later, I started using variational autoencoders and deep neural networks to develop surrogate models for topology optimizations used to encode structural heuristics in agent-based models. For the past 3-4 years, my focus started to shift towards creative AI, and I'm going to talk about those ideas during this lecture. So creative AI explores the potential of teaching machines to interpret, to perceive, to be creative, to propose new building designs, to augment design workflows and augment designers' creativity. While developments in AI means that computers can be trained on certain creativity criteria, the degree to which AI can develop its own sense of creativity is still something to inquire about. Can AI be taught without guidance how to create? Can AI be taught how to interpret things? Can AI be taught how to reinterpret representations from one domain to another, like the way architects are inspired by concepts outside of their architectural domain? So teaching computers to create or to be creative, it's inherently different from the way people create. Although, if we think about it, we don't know that much about our own creative methodology. So although AI in architectures is relatively a new field, it's already producing promising results that are bound to shape our discipline. In this presentation, I will show us a very small part of some of my experiments dealing with these topics. So mainly I structured the presentation in 4 main categories or chapters. One addressing theoretical ideas regarding machine intelligence and creativity, trying to address and clarify some things that I personally see as misconceptions and misunderstanding about AI when it comes to designers engaging with those topics. So it might be that the first part is going to be a bit theoretical and going to talk more about the way machines perhaps understand certain things and not so much architecture. But then the second chapter is going to focus on this kind of idea of holistic design methodologies through agent-based systems and creative AI. A third chapter is going to address briefly the project Copion Blau. Then the last is going to address the project Gaudi plus neural networks. So in this presentation, you'll hear me talking about machine intelligence and machine creativity, which although has similarities to human intelligence and creativity, it should not be equated with the latter. It should be understood as a limited form of intelligence and creativity that is different from human intelligence and creativity. You'll also hear me use AI as a term quite a lot, probably. So just be aware, I'm referring to, when I'm saying AI, I'm referring mostly to neural networks. My research and all the kind of experiments that I'm engaging with, they revolve around deep learning and neural networks. So another disclaimer, in a way, it might be that by the end of the presentation, it might be that we are going to end up with more questions that are unanswered than we started with. Yeah. So the presentation is going to be a bit provoking in a way, and I'm going to raise a few questions.
Can a robot turn a canvas into a beautiful masterpiece?
Can you?
So in recent years, there has been an explosion of research, innovative design techniques and experimentations addressing this issue of creativity and artificial intelligence. Because of the rapid pace of advancement in the field of AI, new examples of machines being able to compose songs, paint a painting, write poems or stories, design everyday objects emerge every single week. So these two are two simple or two examples of neural networks being used in art. These results can be understood perhaps as creativity if because we can say that there is a level of novelty involved and there is an appreciation of novelty. That is important because if something is too novel and we cannot appreciate it, then it has no value to us. So these are two artists that actually are quite well known in this field of AI. So of course, we should not ignore in a way from where all this revolution started when it comes to computers and algorithms and AI. And of course, Ada Lovelace has to be mentioned here. She was the first to recognize that the machine, the mechanical general purpose computer of Charles Babbage, that the machine has different or multiple applications beyond just pure calculations. So she was the one actually that published the first algorithm intended to be carried out by such a machine. So if we think about it, all the examples, or those two examples especially that I showed, they would have passed the Turing test, yeah? So what the Turing test is, this kind of imitation in a way game, yeah? So where you have two rooms, and you have in one room a computer and in the other room a machine. And outside the room, you have a human that sends a task in a way towards the machine and towards the human, and then receives in a way the answer. And the idea is if the human outside the rooms, if that human cannot tell the difference between which message comes from the machine and which one comes from the human, that will assume that in a way the machine has a level of intelligence and it's able to imitate in a way human intelligence. So the idea, of course, here is again like those examples that I showed. Are they actually intelligent? Yeah, whatever machines they were used or networks, are those machines intelligent? Are those machines creative? So we are going to follow along this line of inquiry in the following slide. So when it comes to Turing, he argued in his seminal paper, Computing Machinery and Intelligence, that we have no way of knowing whether another entity thinks the same way that we do. So the only way we can judge the intelligence is by behavior. Turing proposed that if a computer were able to converse with a human being so effectively that we could not tell if it was not human, then we will be forced to conclude that the computer is intelligent. In doing so, we are holding it to the same standard that we ourselves use. So if we think about it, when we converse with another human, I'm unaware of the processes that his or her brain is engaging in to produce an answer that I personally register as being intelligent, but I can judge the answer by its behavior. I must accept that person as intelligent because that person's behavior is on a level similar to mine. Turing, he's also asking this question: can a machine be allowed to carry out something that can be described as thinking, but which is very different from what a human does? So why I'm raising these questions, because very often when we deal with AI and we try to engage with AI, very often we are always confronted with these questions like, but AI is not really creative, it's not creative like humans. So that's why at the beginning I was mentioning, here is not meant, in a way, when we talk about machine creativity, it's not meant to equate it with human creativity, but there are certain maybe similarities in the way that the two types of creativities, let's say human versus machine creativity, how those work. Yeah. So if we think about also when computer scientists first endeavored to teach computers to see, they took it for granted that computers are going to see exactly like humans are seeing. And of course, they were quite wrong, actually, because machines identify numbers based on pixel relations patterns. They don't perceive, in a way, numbers the same way that we do. Very often we are getting stuck in these kind of questions. Can the machine truly see? So I think that's quite irrelevant. So once again, in the words of Alan Turing, can a machine be allowed to carry out something that can be described as seeing, but which is very different from what a human does? So for myself, I think one of the most important shifts that we are experiencing currently, and we have to talk about, is this aspect of shift from expert systems to learning systems. So artificial intelligence as a field, it's quite new, depending now how you calculate that. Could be that it's dating back something like 120 to 150 years. If it's 150 years, that means we are including also principal component analysis as part of the statistics, yeah? And like that, then we can consider AI as being 150 years old in a way. But it has two main approaches to developing artificial intelligence. So one, it's expert systems, and the other one, it's learning systems. So for me, the question is always here, which are going to be the implications for architectural design of this shift from expert to learning systems? So it's important to understand the context of this development, what questions were raised and when. So I highlighted, in a way, the key questions like the Turing test and then the Chinese room problem. That Chinese room problem was presented in 1980s by John Searles, and Turing test was 1950s. And then other developments are the technologies that are really almost like milestones, like such as Deep Blue competing with Garry Kasparov, and then you have IBM Watson competing against US quiz show Jeopardy, and then AlphaGo, of course. So if we think about which is the distinction between the two systems or types of systems, learning systems derive solutions from raw data. Rather than getting hard-coded solutions, they learn solutions from first principle. Whereas expert systems are based on logic systems which feature hard-coded solutions. Expert systems are unable to generalize to these differences, and they are limited to pre-programmed solutions, making them unable to have solutions to unforeseen conditions. So learning systems on one hand, on the other hand, can generalize and offer solutions to new conditions. Expert systems are great when you use to solve sequential problems with finite steps. Learning systems, on the other hand, are most effective when you want to find insights that you may not even know about, when you have a significant amount of uncertainty in your problem. So one question we might ask is generalization a measure of intelligence? So generalization is a key concept in learning. In a psychological perspective, or from a psychological perspective, generalization is observed when learners engage in the skills we teach them in untrained but similar conditions. So for example, Adel continues by explaining that, for example, if you have been teaching the learner to engage in problem solving and the learner begins to independently solve novel untrained problems, generalization has been observed. So in AI, generalization refers to your network's ability to adapt properly to new previously unseen scenarios. And if we are applying the same standard without necessarily creating an equivalence, a machine or a human capable of generalization is considered more intelligent than a human or machine that is not able to generalize. An example of expert system, of course, is IBM Deep Blue. And I'm going to try in a way to not debunk, but in a way to clarify certain things that I find as misunderstandings when it comes to these examples. So nothing in the knowledge base of Deep Blue will help you do anything else besides playing chess. To play another game, it will have to be reprogrammed. So it has this hard-coded specialized system that it's only good at one thing, playing chess. So in terms of thinking about intelligence, something was missing here. The notion of learning and the notion of generality both are missing from Deep Blue and expert systems in general. So is this machine intelligence? Is hard-coded knowledge machine intelligence? The other example of a learning system, of course, is Alphago. So Go has a history of about 3,000 years, and it has more than 40 million players. So Go, it's hard for computers to play because of its enormous search space of possibilities, 10 to power of 170 position. The search space is so much larger than it's much more larger than the search space of chess. So it's predicted in a way, or estimated actually, that there are more possible combinations on the board than are atoms in the world. So Deep Blue uses a technique known as evaluation function. So these are in a way rule-based algorithms that notify the machine which side is currently winning the position. As a result, Deep Blue is able to determine what is the right move to play next. The challenge with Go was that Go is such a complex game that it will be impossible to figure out which are all the sets of rules and hard code them into a rule-based system. Even if you ask top players of Go, why did they make a particular move, they will often tell you that it just felt right. They will also be able to tell you explicitly why they won't be able to tell you explicitly why they made that move. While if you ask a top chess player, they will most likely have a specific plan that they were thinking about. So in Go, it's most like a feel, more like an artist will feel. So Go is primarily a game about intuition rather than calculation, which is more dominant in games like chess. So that's how Go professional players deal with this kind of enormous complexity and this evaluations function. They are really relying on their instincts and their intuition. So AlphaGo is designed by having a structure composed by three networks that interact. So you have a policy network, which is a neural network, you have a value network, and you have a tree search, which is a Monte Carlo tree search algorithm. On one side, the value network provides an estimate of the value of the current state of the game. What is the probability of the black stone to ultimately win the game, given the current state? The output of the value network is then the probability of a win. Yeah? On the other hand, the policy network provides guidance regarding which action to choose given the current state of the game. The result is a probability value for each possible legal move, where higher probability values correspond to actions that have a higher chance of leading to a win. So the two networks are continually learning by playing a game against itself. And the last component of this, of course, is the tree search, which looks through different variations of the game and tries to define which move is most likely to succeed. So the policy network scans the position to identify interesting spots to play, and it builds a tree of variations and uses the values network to determine how promising is the outcome of that particular variation. We can all think about what is creativity, but we can play perhaps the original move in some sense in Go, and without necessarily knowing that well to play Go. We can place random stone on the board, and that could be surprising some ways. So a move is only considered original or creative only if it ends up being effective. And you can measure effectiveness and evaluate it if that specific move had a material difference to the outcome. So of course, probably many of you that are familiar with the story of Alphago, there is the move 37, where Alphago really, in a way, almost like proved that it's able to be creative. Now, a misunderstanding that I want to clarify here when it comes to Alphago is this aspect of many people are just saying, well, Alphago just applied brute force to evaluate all possible moves. And by applying, in a way, that kind of brute force, it can predict all moves that will succeed. So the argument, therefore, being that AlphaGo cannot be intelligent and it cannot be creative because it's just a brute force. So there are a few problems with this. It might be that the misunderstanding stems from us being used with the logic of expert system. It might be that we still judge AlphaGo, which is a learning system. It might be that we still judge that system as an expert system. Or even more importantly, it might be that we don't actually understand how deep learning models operate. So first point here. So the search space of possibility, or why do I think AlphaGo, let's say, didn't use brute force, is the search space of possibilities 10 to the power of 170 positions, yeah? So that means to even try to calculate all the potential permutations, you'll have to take all the computers in the world and run them for millions of years. And that will not be enough compute power to calculate all the possible permutations that you have in Go. So for me, the question is that how can it be then that AlphaGo, it's brute force? And the other point here that I want to make is the misunderstanding demonstrates a lack of understanding of how neural networks learn. It's not a brute force approach because the final learning is not a step-by-step process and is not solved by exploring all possible neural network weights. Rather, is it solved from an optimization point of view, which aids to discover optimal weights via gradient descent. So if we are familiar with the idea of gradient descent, we understand that it's mostly about optimization or optimum, in a way, path than searching for all the possible weights. Yeah. But on the other hand, Deep Blue, which is an expert system, is an example of AI that uses brute force. So for example, Deep Blue, it's a specialized purpose-built computer capable of examining 200 million moves per second or 50 billion positions in the 3 minutes allocated for a single move in chess game. So both games, we can say that they would have, or they have passed in a way the Turing test. But again, are they intelligent? Are these machines truly creative? This question is something that we've been trying to answer for a long time. And Alan Turing proposed in a way this kind of idea of measuring intelligence in the Turing test without actually defining what intelligence is or how we can describe that intelligence. If we fast forward in a way 20 years later, after the Turing test, John Searles in his paper Minds, Brains, and Programs raised this question known as Chinese room problem. So again, it's important to understand the context of these developments, what questions were raised and when. Searles' Chinese room problem seems to be a question addressed towards expert systems, which were the dominant mode of operating AI during that period, like 1960s and 1980s. So this distinction is important. In philosophical discussion on AI, the Chinese room has pointed to the fact, or is pointing to the fact, that when expert systems, which are rule-based, were popular back in the 60s and 80s, that having some rules does not constitute AI. So mostly this is what the Chinese room problem tries to explain. Yeah, just because you follow a set of rules, that doesn't mean that you're intelligent. Yeah. So how the Chinese problem or Chinese room problem is described. So you have a person in a room that is non-Chinese. This person is not a native Mandarin speaker. He or she does not even know where China is. So this person doesn't know anything about Mandarin. Yeah. So in this room, you have also some books. You have one book which is a dictionary of Mandarin to English, which contains every word in both directions. And then you have another book which contains millions of rules. And this non-Chinese person has been trained to use a dictionary, follow the rules one by one, and then this person can basically translate any Mandarin text in English. So from outside, people come and put in Mandarin text, and out comes English text translated. So John Seals, he poses these questions. So after he creates this kind of hypothetical Chinese room, yeah, these are the questions that he's asking. So can this person understand Chinese? Yeah, only because that person is able to follow certain rules is that person actually understanding Chinese. And then I think the most important question is, can the room understand Mandarin? So we are going to see, try to see if we can address these questions. So here I would like to address also a problem here with the way that we use design, or the way we operate with AI in design. As designers, we engage with AI, neural networks, GANs, etc. We are convinced in a way that we moved away from this kind of expert systems like parametric design or other computational design tools that are mostly rule-based. We have this GAN architecture that are deep architectures. We feed them with a lot of images, hundreds, thousands, or hundreds of thousand images examples. And then these deep architectures can learn the representation of the data that was presented to them. So the question is your model generalizing well? So what is happening if your model doesn't generalize? What is happening when your model is overfitting, which means memorizing the data that you input? So if your model is overfitting, it means that we are back in the Chinese room problem, as using rules does not constitute AI, yeah? Because this is what overfitting is. You're mostly just following rules. You're just memorizing things. You're not learning the first principle in a way, the concept or the generalization of an idea. So we cannot say that there is intelligence there, yeah? If your model follows memorized rules, yeah? Might be that some designers will make this kind of argument that when working on creative tasks, the issue of overfitting or underfitting a network is not that concerning, as value can be found in artifacts generated by a badly trained network. So for me, that sounds great, and that might be the case, and I have no problem in a way with architects searching in a way for this kind of artifacts or this kind of mistakes and errors. But for me, there is still one question that bothers me. It's great that you want to find novelty, I believe, yeah, in these kind of strange outcomes. But my question is, why do you need deep neural networks for that? So I usually use this comparison. So how is it then different from a blender? You input thousands of images in, you spin it up, and you get something interesting, strange results. A machine that overfits is no more creative, intelligent than a blender that simply just spins up what you put in without learning any relations between the elements you put in. So we are used to this kind of hunt for artifacts that different technologies we engage with generate in this quest for finding, in a way, the novel solution. But I believe to surrender to that kind of mode of operation is to negate the learning system's potential. We reduce, in a way, learning systems to some generators that might create some artifacts, what we might consider novel. So it's a big misuse, in my opinion, of the technology potential. So let's see, let's try to create a simple system to see how a intelligent system might look like. So let's say that we try to create a simple system that has a degree of intelligence, and imagine that we try to create a model that is able to play tic-tac-toe. Yeah. So if we were to create an expert system, first we want to create a lookup table where we define all the rules of the game. If the condition is met, then set this. Yeah. If this condition is happening on the board, then you have to do this. Yeah. So we are pretty much hard-coding the rules of the game into a lookup table. And second, then we just have to create a sort of mechanism that is able to look at the current position on the board and then read the condition, look at the lookup table and see which is the next move that has to be made, yeah, which is the rule that applies, you know. So this is what Deep Blue, actually computer that defeated Kasparov, this is what exactly the computer did, yeah. You look things up in a lookup table, you look things up very fast, you have millions of rules, but because of compute power, you can go through those rules extremely fast. So it's speed then intelligence, it's knowledge encoded in lookup tables, intelligence. So let's try to look at the learning system, like let's try to create a sort of learning system. So first, maybe we say, first, let's say that we want to understand the state of the game, yeah? You want the system to be able to have a generic understanding of the game. You're not interested in the very particular position and specific. You want to have the system somehow understanding or having a general understanding of the game. So we are looking then, the next step will be maybe we are looking to develop a mechanism to identify current board position, which might be similar with step B from an expert system, for example. And then maybe we think, what is the situation on the board? Yeah, can we have a way to evaluate that? What are the next possible actions? We don't want to take explicit actions in a way. We just want to understand the game. Yeah. So which are the next legal possible moves? So intelligence means that you have a general concept, a general understanding. Yeah. So we want then the last step, perhaps we want to have an evaluator. So we want to evaluate some of the game as such. Yeah? Tell me the state of the game and then evaluate the game. So the two examples are very similar to the way AlphaGo and Deep Blue are structured. One is static, specific, and hard-coded, which is non-intelligent, as simply following rules does not constitute intelligence. Yeah? And the second one is dynamic, generic, and implicit. And it's intelligent as it tries to learn a general concept of a game. It tries to generalize, yeah? So although AI can exhibit in a way this kind of forms of intelligence and intelligence as machine intelligence, I'm talking about machine intelligence, and maybe also a form of creativity, we should be careful not to equate them with human or human creativity or human intelligence. So Demis Hassabis, the creator of DeepMind, identifies three types of machine creativity. So we all know that neural networks, they are very good at interpolation. They are this kind of massive statistical machines, and they are very good at averaging things out and spotting patterns in data. So in this instance of interpolative, in a way, creativity, what you have mostly is you can make the assumption that if you have 3 points display, or in this case, you have 6 points display or 7, if you just average out those 5 points, you're going to create a new, in a way, design, let's say, if those points represent design, which is just an average of all the designs that you have there. Yeah? But the idea is that this kind of mode of operation, it's confined then to that input data that you have there. Yeah? So it's just interpolating between data. So the other form of machine creativity that Hassabis defines is extrapolation. So the idea will be can you have a network that is able to go outside of the knowledge that was learned through the data set, yeah? And Asab is now, probably he's biased because AlphaGo, it's his creation. He's making the argument that actually AlphaGo, through that move, through the move 37, proved that it's able to extrapolate, yeah? Now, of course, the other type of creativity will be invention, and that will be almost like you invent the game of Go, yeah? So it's not only that you invent a completely new rule that you were never in a way exposed to, or you never saw that move. It's you're creating the Go game actually. So of course, when we talk about machine creativity, there are a lot of things that are missing, like understanding concepts, abstractions, analogies, or memory systems or imaginations, or all those topics in a way, for sure, they are not currently present in AI systems. So what AI established above all else is that every possible form is already out there, and it's simply a matter of searching for it. So this is Costa's in Permutation Design book, yeah? So we are talking quite a lot about this kind of idea of artistic creativity. But if you think about creativity in other domains, like scientific creativity, they are producing this kind of beautiful new theories in mathematics or physics. So it's not clear to me, once you start talking about these formal domains, to what level creativity is not actually a form of meaningful random search and basically structuring how you're searching for the right things. So certain people have a talent to shape in which direction they are searching for new things. So if you talk with digital composers, they will start with a random music string, and then they will try to enhance them from there and just walk like that through the entire process, yeah? AI can help us to shape the way we are doing meaningful random search and explorations. So that's why I think it's important to have machines that have a form of intelligence and creativity, because otherwise, like a machine is not going to help at all if the machine actually just creates even more noise and even more randomness in this entire process. So if we are looking also back at this kind of idea of AlphaGo, so AlphaGo, it's a system that learns. It's not a system that tries to, through brute force, is trying to find a solution, yeah? So it has to find a good solution with a limited amount of compute in this kind of vast search space. So I think as designers and creative and humans, we are faced with exactly the same problems. Especially in architecture, we are dealing with n-dimensional problems and problems that are not non-linear. So then, can you use, in a way, machines to help you navigate these kind of spaces? So if that's the question, then you cannot talk about a machine that is not learning. You cannot talk about a machine that doesn't have a form of intelligence, and you cannot talk about a machine that is not creative, because then the entire engagement with the machine is not really useful or meaningful, because the machine is not really helping you. If the machine is not generalizing, the machine is just creating noise for you. Yeah? So it's not helping you to explore the unknown in a way. So of course, this idea also Neil H. Is talking about this idea in one article in LA Frontiers. It's merely a question of conducting the right search. It's not about the designers inventing some new proposal by drawing upon his/her genius, but rather of selecting the best solution from a range of existing possible options. What use do we have then to engage with these kind of very sophisticated learning machines when in the end the results are evaluated by human beings? All the results are going to be constrained by our own limitations, if you think about it, yeah? So here, the example from Lise Doll with AlphaGo, he mentioned this. What surprised me the most was that AlphaGo showed us that moves humans may have thought are creative were actually conventional. So of course, the human agent in all this process is very important, but very often we are we consider ourselves as being creative, and very often we are actually, we are not. Very often we consider that things that we are doing are creative when in fact they are very conventional. So everything we hear, see, or read makes sense for us in the context of what we know. People evaluate these outputs based on things that they already know, they are familiar with. And when they are faced with the unknown to them, they may think that those things are new, but are they actually new? Are those actually the correct or the best solutions? So this is the graphic here. This is what it's trying to address, yeah? Very often we are saying that we are creative, and we are not aware in a way that we are defined by a very limited search space, and that actually we are operating into a local minima of a solution, yeah? So can machine in a way help us explore this unknown and help us understand the other solutions that are out there and expand in a way these kind of moments where we get stuck perhaps in this kind of local minima? And of course, this topic of what exactly is novel and what not. If something is too novel, we can't appreciate it. If it's too unexpected and too unrelatable, we cannot appreciate it. If it's too similar to what we already know, we still don't appreciate it. So there is this kind of sweet spot in a way between there. But for me, the question will be, can we somehow use this kind of machines to help us understand actually better solutions? Because right now we are just looking at the results of an AI and we constrain those solutions based on what we think that's correct, yeah? Can, in a way, AI help us explore the unknown, yeah? So of course, I'm going to move a bit fast through this because I see that we are already 40 minutes in. So this idea of design, that how you explore design, is very important. And can we use AI to help us explore design? So traditionally speaking, that's how you will start designing. Yeah, you start from an empty piece of paper, then you start draw a stroke, and then from there you continue and develop a design. Yeah, but in my understanding, I see design. You have this expression, hunting a needle in a haystack. But I see design as hunting a needle in a flock of birds that constantly changes. Yeah. So what I mean by that is you always have this kind of, you take a decision, the design space either expands or contracts, yeah? Or you take another decision and design space either contracts or expands, yeah? So you have this kind of like design space in a way that it's always alive and changing, yeah? So the idea then will be, can you have this kind of network where you're just saying, one design here, one design there, just a very rough, in a way, idea of what the design is or should be, and have an AI, in a way, fill up, in a way, the gaps between those designs, yeah? And help you, in a way, explore in that kind of manner. Can it be that, let's say, you're just showing a very rough sketch that is not that proficient, in the sense of is not accurate, but can you do that and then have the AI, in a way, develop it into a product that is refined, yeah? So the same here, the same idea, but here then the question is, how do we encode then this kind of knowledge in these kind of systems, into these kind of AI systems? How can we make them machine readable? Yeah. So in this instance, I'm using agent-based systems exactly because of this reason, because it's much easier, in a way, to encode intentions through this type of system than another type of system that's out there. And once you have then the network, in a way, learning, you can create, learning this kind of intentions, yeah, design intentions, creates for you this kind of design space that you can explore. So I'm going to go now through the three projects very briefly then, to just give an idea. So this methodology consists of a holistic approach to design processes in which a variety of interconnected neural networks strategies coupled with agent-based systems are deployed to address different architectural design tasks. The methodology develops on system theory, where that sees, in a way, architecture as being composed of these kind of multi-systems that are interrelated. So here, this idea also follow along this idea of after he lost to Deep Blue, Gary Kasparov, he started to research in a way if there are certain ways how we can enhance human intelligence and improve players' competitive advantage. So he discovered then that a weak human player plus a machine plus a better process, it's way superior to a very powerful machine alone, and way superior to a strong human player plus machine and inferior process. So I think this is a very important aspect, because you want, in a way, to have a dialogue with that machine. You want the machine to augment. You don't want to just automate design. So then here, a lot of topics of how you interact with the machines are going to be addressed. So in this instance, this project, it's really structured in 3 main phases: explore, qualify, and generate. And for each phase then, you're developing AI workflows that allow you in a way to explore design at different levels and different design tasks at different level, and then evaluate them, and then qualify them, and then generate. Of course, my goal here is not automation, it's augmentation. I'm interested in augmenting design potency. I'm interested in augmenting designers' native abilities. But certain steps are going to need, in a way, automation. For example, structural heuristics, they require, in a way, they require then automation, so that you have this kind of real-time feedback then between the systems. So here you just see then walking through this kind of very complex design process, where for every single layer you have different kind of questions that you're asking. Therefore, you have different kind of networks that you have to operate with to answer those questions, yeah? And then you have this kind of qualifying phase where you're developing, in a way, ways to evaluate the results. Because the promise of computation, for example, is this idea of we are going to be able to create variations, and we are going to be able to see like thousands and thousands of variations. And the problem with that is that as humans, we are not capable to look at the design and evaluate the design against 10 or 20 criteria. Yeah, it's very hard. So imagine then if we have to do that for 100 designs. Yeah. So then this system, or this kind of logic of chaining networks, is trying to do exactly that. So you generate with certain networks, and then you evaluate and qualify with other networks. And once you have these 2 types of networks, one that generates and one that qualifies, then you can say, okay, I have a network that gets this information from explore and from qualify and starts to generate design. Yeah. Because it's going to be informed by those aspects of exploration of design, and also aspects of qualifying, like qualities and so on. Yeah. So here, then the process goes from this kind of 2D, because maybe some design tasks, they have to be addressed 2D. But then you also have tasks that have to be addressed in 3D. So in this instance, you have an example of a network that I developed recently that works in 3D. And soon this network is going to be published. And here you have the same kind of idea of qualifying. So you're looking, in a way, and help or using AI to help you sort and classify and narrow maybe your search space, or help you navigate the space. Okay, so these are like the kind of aesthetics that we solve, but that's not the focus there. The focus is mostly on this design process that you're augmenting with this kind of neural networks. So I'm going to go briefly through DigitalFUTURES. So DigitalFUTURES is a project that we are working on at DigitalFUTURES, and currently this is the team from DigitalFUTURES that works with DigitalFUTURES: Wolf Briggs, Caroline Schmidt-Bauer, myself, and Filena Baseta. So DigitalFUTURES as a style is very diverse. So the question then is, how do you train, and how do you teach the network to learn in a way that is not biased towards buildings that are more represented than other? So here, this is what you see. The initial data set was something like this. So how can you in a way design that network in a way that it's able to give the same importance to all the projects. Yeah. And here we have then this kind of explorations, idea of explorations, how you explore design and so on. So this one, yeah, seems like it's not playing. We are already working in 3D, and this is very recent actually development. Until now, we were very focused on this aspect of Gestalt in a way, and we were mostly interested with images. And now we start to go towards aspects of organization and 3D. Yeah. So in this instance, we are talking about the type of creativity of the network that is mostly interpolating. And we might expect that all the results that we get from this kind of network are confined in a way within the data set that was presented, yeah? But even in that kind of scenario, the design space generated by the networks or the latent space is vast. So the idea is, how do you engage with it? How can you take advantage of this kind of vast design space that gives you so many possibilities? How can you take advantage of that and help you enhance your design decisions? So we are looking at different ways how we can do that. And I'm just showing here 4 methods, and I'm going to go quite fast through this. So we have latent space explorer, latent space explorations, which are mostly algorithmic processes, latent space projections, latent space queries. Yeah. So when it comes to latent space explorations, the idea is, how can we have our designers in the office engage with the network? Yeah. You don't want, in a way, this kind of problem where you have to teach the designers to be proficient in coding or something. Yeah, how can we make this interaction between humans and machine very frictionless? Yeah. So then here there are just a few methods that we are engaging with. Yeah. So in this case, you are just selecting then in that kind of latent space explorer, you're just selecting a few images and they show up. Yeah. And like that, you can visually, in a way, explore things. Of course, we are doing the same thing also when it comes to floor plans. We are looking at all those aspects, and also when it comes to 3D. Yeah. So we have these kind of latent, large latent spaces that we can explore then 3D floor plans and Gestalt, which are just images. And then we have methods which are more algorithmic, and these are not so friendly then towards designers. And we are working on interface of how to create an interface that is friendly, so that designers can also engage algorithmically in a way with this kind of design spaces. And in this instance, you're just querying in a way for nearest or the closest similar images, and then you're just going from very similar to very dissimilar. And then this kind of idea of projection, it's almost like the network, when you look at the result of a network, it's almost like the network projects in your mind an image, and then you interpret that image and you understand it in a certain way. So the same thing happens also here. It's just that reverse. We are reversing the direction. But as you can see, the machine is not really that imaginative in a way. It's really taking it a bit literal. So then, of course, we are looking also at this more pragmatic, not pragmatic, but more simpler ways of interacting. Like, can a designer just type in a sentence and have from this vast design space sort and extract designs that are described by that sentence? Yeah. So in this case, we are saying an irregular shaped office tower. Yeah, so we have 0.29, the highest value, and if you look at the image, the similarity between the image and the semantics of the sentence are actually quite close. So we do the same thing. Then we can do like with a vast amount of sentences or the entire design space. Yeah. And then we can also like be very strategic and say we're interested in a tower with glass facade, tower with apparent structure, tower with a plinth, tower with this or that. Yeah. So we can really be very intentional then in our search. So the idea here is not necessarily to generate images or designs through text, The idea is we have a very intricate, in a way, network that we design to generate and to understand our style, yeah. And now that network is able to generate for us this kind of vast design spaces. And the question is then, how do you query that design space? How can you explore it? So the same happens here. So you have this kind of sentence, and then from there you have. So I'm going to go quite fast over this also. So the Gaudi neural networks is trying to address this architecture problem. It's an ongoing research that looks at the development of neural networks capable of identifying relevant compositional features in samples representing Andoni Gaudi, Sagrada Familia, and samples from nature. So there are meaningful tectonics defined by Sagrada Familia that are constrained to typical nave symmetry and seriality of the underlying composition. And the goal here is to deploy deep learning strategies in order to liberate the intricacy, in a way, and novelty of the structural properties found in the tectonic detail. Yeah. So this kind of development of strategies will enable this kind of intricate tectonic detail and structural property to be played out on more complex compositions. Yeah. Compositions that are more free. Yeah. If we talk about floor plans, for example. Yeah. So when it comes to data, the generation of training data can be seen in a way as this kind of process in which we as humans, we are transferring our knowledge, reasoning that lives within our brains, yeah? And we are transferring this in the machine. So in that sense, we can say, well, the machine then it's just an empty shell, yeah? Without that kind of data, it's just an empty shell. And that's pretty much what it is, yeah? A machine without data is not much, yeah? So similar with parametric design, where design possibilities were predefined a priori, relying exclusively on data sets as the main form of encoded design intelligence and design intentions lead to very constrained setups. You know, it's almost like for me, I have this kind of fear of what we are doing. We are just conserving, in a way, all back history, in a way, all historical, in a way, examples. When in fact the goal should be, how can we learn something? How can we learn certain insights, extract those insights from that, and then apply them to new design strategies or new or figure out ways to come up with completely new solutions that can be useful in today's society. So are we simply engaging in a process of preservation of known solutions? Or are we looking for something that can generate solutions outside the given domain and expand our understanding? So here I started also to look at this aspect of the machine, or the way that we as designers operate. We have a certain constructed, in a way of understanding things, which is influenced by our past experiences, the way that we were trained as architects and so on. This idea, it's also presented in Derrida's, in a way, work, this kind of idea of a reality, or we understand things in a constructive way. So I'm looking then at different ways how to engage with these networks and how to extract the relevant information and how to design the networks in such a way that that kind of relevant information is extracted. So here I'm looking at different kind of resolution, what it means, the perceptual resolution of the network, what influence that does it have on the learning and so on. Yeah. And then, of course, this aspect of, again, like, can we also explore some ideas just with this kind of network? Like, can we just type in, for example, here I have multiple networks that are interconnected, and one network is responsible for the compositional level. The other one is for responsible for a more refined level, and then you have another network that is responsible for this kind of translation, in a way, of the semantics of Sagrada into the composition. Yeah. And the same effort happens also here when it comes to 3D. So trying to shift now from a just purely 2D approach to a 3D approach, where certain information and certain semantics can be learned in 2D for sure, but can we also learn from 3D and maybe start to compare and see how we can develop this. All right, so this is going to conclude my presentation. So my apologies for running a bit quite long with this. All right, so this is the last slide. Thank you, everyone. And thank you for all the questions that you're going to have. And I'll be more than happy to answer any of your questions.